Today we will discuss thermodynamics of electrified interface. As we know, this is the equation for closed systems where there is no exchange of energy and matter, and this is the equation for open system. So here in this there is summation of mu I dna, where mu I is chemical potential. Now the work done at electrode and electrolyte interface will be given by following terms. The first one is PdV, that is work done in expansion of volume, that is dV against the pressure. Gamma dA, work done in increasing interface area against interfacial surface tension. And this is phi dq, work done in transferring the charge dq m from external source to interface against the potential difference, that is del phi. And this is mu dni. This is work done in transferring the mole of species I against chemical potential. So the equation becomes this one, that is du, which is internal energy, is equals to TdS minus PdV minus gamma dm minus del phi dqm minus summation mu I dni. Now here this equation is multiplication of two properties, intensive as well as extensive properties. This is T and ds, where T is the temperature and change in entropy is ds. So this ds is the variable term, which is extensive property, which depends upon the number of molecules, while this temperature is intensive property, which does not depend upon the number of molecules. Similarly, this PdV, where dV is extensive, P is intensive. Similarly, del phi dqm, where dqm is extensive, del phi is intensive. Mu dni, where dni is extensive and mu I is intensive. So this equation is factor of two properties, intensive as well as extensive properties. So this equation, if we write this equation, then it will be like this equation. When we differentiate this equation completely, then we come to this equation. Now if Ts, if this is the equation, du is equals to Ts minus Pv gamma a minus del phi q dash minus summation mu I ni. If we differentiate this equation, then we will come to this equation, that is du is equals to Tds minus Pdv minus gamma dA minus del phi dq minus summation mu I dni plus St minus Vdp minus A d gamma minus Qm differential of this del phi minus summation of Ni d mu I. So this is the complete differentiation of this equation. Now, since we know that this du equals to this one part, so this will be this part or first term of this equation, right hand side equation, will be equals to du. So du is equals to du, which will be cancelled out. Then the remaining equation will remain like this one. So this equation will turn into this equation. If in this equation, if we make two things constant, that is temperature and pressure, then this this term and this term will be zero or constant. Now this equation will turn into this equation. that is 0 equals to minus a d gamma minus q dash d del phi minus summation ni d mu I. After rearrangement of this equation, we will get this equation. Rearrange this equation. So rearrange this equation. This a d gamma is equals to minus qm dash or prime del phi minus summation ni d mu I. Now, if we rearrange this equation, we will come to this equation, which tells us about the change in gamma. So d gamma is equals to minus q dash m del phi over a, since it is transferred to this term as well as to this term, minus summation ni a d mu I. Now here, change in surface tension, this one, is now dependent on two factors, the first one and the second one. That is the potential difference across the interface and the change in chemical potential, that is solution composition. Now, we will talk about the surface access. So this Ni, we have this term. So Ni over A is equals to gamma plus Ni over A. So ultimately, this term, what? This one is replaced by gamma d mu I. So this is what? This is nothing but the surface access term. Now we will replace this equation. We will replace this equation by this. So what happens? Equation will turn like this. Now surface tension, or we can say change in surface tension, is related with two terms. Is first, potential difference across the interface. Second, change in chemical potential along with surface access. So this change in surface tension leads to two terms. Okay. Or we can say it is okay, let us explain this one first. So this equation which we have just read have two terms. This change in potential, what this change in potential, we have a concern with change in metal to electrode or metal to solution. So we will write M1 del S. This is solution side, electrolytic side. This is metal side. And what we have, the potential metal to solution, that is change in potential from metal to solution, or electrolyte to metal to electrolyte, or the second electrode, that is solution to metal, and then the two electrodes, that is metal to metal, M1 to M2. But what we will do, we have a concern. We don't have any concern with this metal to metal potential, but we have concern with electrode and electrolytic surface. What? M1S and this S2 M5 del phi. So we have a concern with the second one, that is polarizable and non-polarizable. So we have a concern with the working electrode. So solution to matter. This term now will be replaced and the equation turns into this equation. And when we treat this equation. When we have a concern with uh, the electrode, then this will turn into this one, where J is the particular species involved in the leakage of charge across the non-polarizable interface. So, this equation we are getting as the fundamental equation for thermodynamics treatment of polarizable electrode. So, it is a relation among interfacial surface tension or surface access, surface tension, surface access, applied potential charge density, and the solution composition. This shows the interfacial tension variation or variation with the applied potential. That is, we call Lippmann's equation. In our next class, we will read this, or we will talk about this Lippmann's equation. And second one, it tells about interfacial tension variation with the composition. So this was all about the thermodynamics of electrified interface. Thank you.